In this video, we're going to talk about the transition elements and their properties, going over definitions for D block and transition elements and examples. So first of all, you need the D block elements. So D block elements definition is this. Highest energy electron is in the D subshell. So if we go across here and we look, here is your D block, which is the big yellow block here, and any element which has an electron within that D subshell, okay, is going to be a D block element. So all the yellow ones are D block elements. But the definition, really important, highest energy electron is in the D subshell. Now, if that's the case, let's go through one example and go through the order of filling, because if you have to do a question like this, you're going to have to do the electron configuration. So never do a question like this when you're going through definition without giving an example of an electron configuration. So the order of filling is down here. We've already got this principle here that we've gone through in previous videos where that's the order of filling, but let's make it even simpler, okay, and just say the order of filling is here. 1s, 2s, 2p, 3s, 3p, 4s before the 3d, okay, and that's the order of filling. You can write it out with the 3d first if you want, but you've got to remember the order is filling the 4s first. So I always put 4s before 3d in terms of writing it out. But so important, remember, fill the 4s first. So we're going to have one of the examples. The example we've got here is scandium. So stop the video, try and do it yourself. So try and do your scandium electronic configuration. Now, the important thing here is that when you're going into your second year of your A-levels, they'll write out argon for you in the middle. So you can see I've got argon, and that's the configuration here, 1s all the way up to 3p. So we only need to consider the 4s and the 3d. So we need to think now, scandium. Where is scandium? Well, scandium is right here. So we've got 1 electron per block. So there's 1, 2 electrons in the s. So this is the s. This blue block here is the s. And that's in number 4. So this is 4 here. So that is 4s2. So that's telling me that there's 2 electrons here. 1, 2. Remember, we've got the configuration all the way up to argon here. And then it's 1, 2 electrons here. Now we've got to scandium. So scandium is now here. So each box is 1 electron added. So we've got 1 electron, but this time it's in the D. Okay, and this is 4. But if you remember the order, it goes period 3 or energy level 3, and then the energy level is 3 here. This is a 3D. Okay, so the ones that's being shown at the moment is 3D. Okay, so that's my 3D. But here, over here, is my 4s. Okay, and just to make it clear down here, this bit that's right here, that is my 4p. Okay, so we've got 4p, 3d, 4s. So here we have 1 electron, because it's only 1 box. Okay, so all we do is do 3d1. Okay, and that is how you do the first configuration. We're going to do a few, and we'll do the next few a little bit quicker than this one, but that's how you do the first D block element, scandium. Our next electron configuration example is chromium. So if we're looking at chromium, again, we're going to do the argon. Okay, so that's why we've removed this top, because we don't care about the other electrons. We're just going to call that argon. Okay, and then we go for the 4s2, and then we count along. So scandium, titanium, vanadium, and then we have got our chromium right here. So there's our chromium. So that's 1, 2, 3, 4 boxes. So that should be 4s, 2 electrons, so 4s2, and it should be 3d, 1, 2, 3, 4. But it's not. So it's this. So what you do is you take one of the electrons from the 4s and put it in the 3d5. Now there's some complex chemistry going on here, but in order to make it really simple for you to understand, I'm going to draw the boxes. So here we have, that's my 4s, okay, and then I'm going to draw 5 of my boxes for my 3d. 1, 2, 3, okay, that's 1, 2, 3, 4, and then we've got 5. Okay, so you might have to draw these in the exam or fill them out. So good thing to practice. So stop the video, fill in the boxes. Now, if you look here, I would normally have 2 electrons in here, and then I would have 4 electrons here. But if I can, and this is the way of simply remembering it, it's not the pure chemical reason why, but it's a good way to remember it, is if you have 2 electrons here, they're right next to each other. So if I had 2 electrons right next to each other like that, they're negative, they repel each other, they're going to want to get away from each other. So instead of them having them next to each other, I take one of those electrons, so there's put 1 there, and I place it here. Okay, and then I place in all the other electrons that I had. Okay, so I had 4 electrons from it because I had 4 boxes, 1, 2, 3, 4. So 4 electrons from the D, and then this is my 1 electron from my 4s that's moved over. Now they're now all singly occupied, okay? So they're singly occupied, which means they don't repel each other, lower energy, so it kind of makes sense. But really, really important, remember that this is your exception, could come up in your exam as a 1 or a 2 mark, as part of 1 or 2 or even 6 mark question. Our next example is copper. So you can see copper here, if I go all the way across, copper's right at the end here. So this is our copper right there. Okay, so that means that basically we got some 4s2 electrons and we've got 3d9 boxes. So 4s2, 3d9. Now this is our other exception. Our other exception means that that 4s2 electron moves into the 3d and you get 3d10. So that's a full 3d subshell, and it's an exception you need to remember. So we've got 2 exceptions. We've got the chromium, which is 4s1 3d5, and we've got the copper, which is 4s1 3d10. Both have to be in your notes and have to be remembered. Now, if we go on to transition elements and the definition of transition elements, well, a transition element forms at least 1 ion with an incomplete D subshell. So that has to have an incomplete D subshell, not full and not an empty. That's really, really important. And the electrons are moved from the 4s shell first. That 4s shell, once you put electrons in it, becomes a higher energy, becomes slightly further away from the nucleus, and therefore those electrons are easily removed from the 4s before the 3d. Now, if we practice that in terms of examples, we've cut down again, and we start with scandium. I'm going to go through some exceptions. These are really important for your notes, so make sure that you've got them down. 4s2, 3d1 is what scandium is normally, but scandium only has 1 ion, and the 1 ion is scandium 3+. Now we know we remove the electrons from the 4s first, so we remove it from here first, but there's only 3 electrons there in the first place, 2 and 1. So if I remove all of those electrons, all I'm left with is argon, as in the configuration of argon, which is 1s, 2s, 2p, 3s and 3p, all of those electrons in there. But again, you're in the second year of your A levels, you're in transition elements, you can just put argon. Okay, and that means basically I have no D subshell, as in I have no electrons in that D subshell. That is an empty D subshell. So scandium only has 1 ion, the Sc3+ ion, and it's got an empty D subshell. Therefore, it is not a transition element. That's our first example. If we go to our next one, you can see here we've got zinc. Now zinc, got 2 of those 4s electrons, and then it's all the way to the other end here. Here is zinc. Okay, and so that's 10 boxes, so 10 electrons in the 3d. Now if that's 10 electrons in the 3d, that means if we want to make it into an ion, the only ion that exists is going to be zinc 2+. So we're not going to get a zinc plus or anything like that, okay, that you deal with in your A levels, okay? But even if we did, both electrons would be removed. All of these electrons would be removed from 4s, because the electrons are removed from the 4s shell first. So that means if those electrons go, we're left with a completely full D subshell. So zinc 2+ is just argon with 3d10, completely full 3d subshell. And if that's correct, it's not incomplete. And because it forms that zinc 2 plus ion as a full D subshell, it's not a transition element. So let's have a look at both of those now. So again, in your notes, make sure you've got these two elements that are not transition elements. But the rest of them in level 3, in energy level 3, which is the ones you deal with most of the time. We're not going to talk about the ones underneath because they're not really used particularly. They are all transition elements because they have more than one ion. And we'll talk about that further in further videos and show you all the colours as well. Now, just make sure you have it in your head. Scandium and zinc are not transition elements because that full and that empty D subshell. Now, if we look at some other examples just to show you how actually they are transition elements, we can look at chromium. Now, chromium's got a 3 plus, it's also got a 6 plus as well. Okay, so it's got multiple ions. But just for this ion here to show you, you can see that we remove the 4s first, because you've got to remove 3 electrons because it's 3 plus. So remove the 4s, and then that 5, I have to remove a further, and there we go. I have to remove a further 2 there. So that means basically you have lost your 4s1 and 2 of your 3d electrons to go to 3d3. Now that's often missed in exams, okay? So I'm going to go back. Now remember, that is the exception. So they're starting with an exception. It's chromium 3 plus. You lose 3 electrons, 1 from there and 2 from there. So basically that's all I'm doing, but you do it in that order. And there's your argon 3d3, a very common example. So let's look at another one. This time we've got copper. Now copper can exist as copper plus, but it can also exist as copper 2 plus. So it's got 2 ions that we generally deal with. Copper 2 plus, okay, is where you take that 1 electron from the 4s and you take the second electron from the D, which means you have an incomplete D subshell. So both chromium and copper have the incomplete D subshell and therefore are transition elements. And this generally follows all the way through. So what I would do if I was you is I would get all these elements and start drawing out the different ions as practice. Now, the thing about transition elements is that they usually have variable oxidation states, or sometimes referred to as numbers. So we can call them states or numbers depending on what you read. Okay, they all tend to form 2 plus ions, and they lose those 4s electrons. Okay, so that means as well, as soon as you've lost those 4s electrons, you will lose the 3d electrons next. And that's how you get all these different oxidation states and numbers. Okay, so if you look here, here is my diagram of all of these charges. Now, I don't want you to think for 1 second that you need to remember all of these charges. We'll go through the ones you need and we'll make it look a little bit better as we go through. So we've got D block elements. These are all D block elements because they all have their highest energy electron in the D subshell. But now let's go through the transition elements, which ones are and are not. So we've got all the colours here. So easily you could pause this, but don't worry, don't do it at this moment because you don't need to remember all of these colours. Now, if you've got it in white, that's generally ones you don't really look at, and when they dissolve in solution, they tend to be colourless. Okay, but we've got some of the other ones which we're going to highlight. So if I highlight all the ones that are really important, these are the ones that are really important. So these are the ones that you'll need to have a look at. So we will go on about them in further videos and show you actually examples of this. Little things like you have got this orange chromium 6, this green chromium 3, really, really important, okay? Manganese, pale pink, going to +7, which is purple. And you've got your iron with your pale green and your pale yellow, and you've got your copper with your blue or pale blue. So all of these, really, really, really important, okay? And you're gonna have to remember them. So what we'd recommend you do is put them on cards, okay, and then have them in your room so that they just go via diffusion into your head slowly over time. But everything apart from scandium and your zinc are transition elements because they've got all of these different ions within an incomplete D subshell. Now, we're going to go through some of the examples of experiments where you can use your transition elements as catalysts. And the most common one that we've hopefully all done in our school life is hydrogen peroxide. So hydrogen peroxide turns into water and oxygen, and the catalyst increases the rate of reaction. So here you have hydrogen peroxide, okay, going to water and oxygen. Now what that does is that will create a really large reaction. Now that large reaction is called a decomposition, but we videoed this in the lab, and there is your elephant's toothpaste. And that's basically just taking the hydrogen peroxide and sticking a manganese oxide into it, and then basically it goes, produces a lot of oxygen, and then what we do is we put a load of washing up liquid in there and some food colouring, and therefore you get this. What you can't see is this is this very exothermic reaction as well, lots and lots of heat coming out. Now, elephant's toothpaste can be done in many, many different ways, okay? But what we want you to remember for this is just the fact that the catalyst is manganese 4 oxide, which means the manganese is in the oxidation number, or has an oxidation number of +4, okay? And it decomposes this hydrogen peroxide. Our second example of a catalyst, which is a transition element, is in the contact process. And the contact process is used to manufacture sulfuric acid and other things. And so basically what you can do is you convert sulfur dioxide into sulfur trioxide, and you'll use this in your equilibrium questions quite a lot. So it's one to become familiar with. It's a good one. Now the catalyst is vanadium 5, now 5 being the oxidation number of the vanadium. So if it says vanadium 5, vanadium is +5 because all of the oxidation numbers of the transition elements are positive. So we've got a +5 oxidation number or state. Okay, and that comes up with V2O5. And again, stop the video, try and work out what the individual oxidation numbers are. And you can use 1, 2, 3 for Huckel, which is how we determine how to do it. And that's in the redox video as well. So sulfuric acid is an important organic chemical with many uses. So fertilizers, so you can use it to make fertilizers to place on the fields. Detergents, really important, adhesives and explosives. Okay, so really, really important, and you'll use it in the lab, in your school, all the time. Now, last thing is car batteries. So if you go into car batteries are based upon acid as their electrolyte that happens. And we'll talk about batteries in terms of fuel cells and things in a later video as well. Now the last one we're going to do is addition reactions, hydrogenation. That's just a reminder, this is in the first year of your A-levels where you take an alkene, you add hydrogen and you turn it into an alkane. Now this is a reduction, okay, because you're adding hydrogen, okay, and in that process of reduction is also gain of electrons. But we can see here it uses a catalyst called nickel, and that nickel is at 150 degrees, 423 Kelvin, okay, but basically this is a hydrogenation. So the catalyst uses nickel. Nickel is a transition element, and so it's a very common thing that's used. So really important when it comes to the exam, what is the common property of transition elements that you write uses as a catalyst, and that catalyst is usually because it can change oxidation numbers in between oxidation numbers. Now nickel in this example is used to lower the temperature and pressure needed for the reaction to happen, which means it saves energy and it saves electricity and therefore lowers cost. But it can also be used and has been done in previous courses and things like that to make spreadable margarines from vegetable oils. So you hydrogenate the vegetable oils.